So I've started recording now. I will reduce that thing. Okay, today we'll be looking at non-parametric counterparts of tests. Yesterday we talked extensively about t-tests, and we did 3 different types. We went through the calculation and how we could use hand to do that, and how we could use the software to run it. So today we want to look at the non-parametric counterpart t-test. You know, we have 3 types of the t-test: one sample t-test, independent sample t-test, and paired sample t-test. The same thing also, the non-parametric counterparts follow almost the same pattern. So we'll be looking at like Mann-Whitney-U test is for independent t-test, independent sample t-test. Wilkinson rank sum is for both. Rank sum is for independent, just like Mann-Whitney-U. But the Wilkinson sign rank is for both one sample t-test and pair sample t-test. The median test, there are 2 types. We have the sign test, which is for one sample t-test, and the mood median test, which is for independent sample t-test. You see, this mood median test is both non-parametric counterpart to independent t-test and ANOVA, one-way ANOVA. When we did ANOVA, we did it also. So it's one type of non-parametric test that you can use for 2 or more groups. 2 or more groups. You know, independent sample t-test is 2 groups, 2 independent groups. So when we are talking of 3 independent groups now or more, we are talking of ANOVA. So it's both non-parametric for independent t-test, sample t-test, and one-way ANOVA. So we'll quickly look at now why we talk extensively about the assumptions for using parametric tests. The t-tests we discussed yesterday are examples of parametric tests, because you assume that the data set follow a theoretical distribution, which is normal distribution, and also other conditions, other assumptions also involved. Apart from that one, the second most important after that is the homogeneity of variance. That is the different group, even though their means are different, and that is why you are testing it anyway. If you know that the means are not, if you know that the means are the same, so there's no need to look for the difference. But you want to be sure that are they actually the different? Are they statistically significant? The difference between the 2 means is statistically significant. That's why you want to test it. So the mean differ, but for you to be able to use parametric tests, the variances must not differ. Even though the mean will differ, the variances must not differ. So that is what we call homogeneity of variance, and the condition is one of the conditions. And the third one we talked about was the measurement must be on at least interval scale. That is, it has to be quantitative variable. When we talk about at least interval scale, we are talking of interval and ratio scale. Now, the last one was the measurement must be independent. The groups, we already established the fact that comparing means, we say you are comparing 2 means. T-tests are not these non-parametric counterparts. They are about comparing 2 means. 2 means. They are comparing 2 means. The mean may be, maybe you have 1 sample or 2 samples, but the issue is that, like if it is 1 sample, you are comparing the mean in your own sample with a theoretical, the one they give you, the one in the population work that has been done before, a particular mean value. The only thing I don't have access to that sample, but you have a mean value in the population which you are comparing with the mean in your own sample. That is why it's 1 sample t-test. But the issue is that there are still 2 means involved. The pair sample t-test, which is only 1 sample, you take measurement before and after. So you can calculate the mean of the 2. You are comparing the 2 mean. Anyway, indirectly, It's not actually the two mean you are comparing. Yeah, you are comparing the two groups. You are comparing the two groups because in the research for the test sample test, which we did yesterday, we realized that you have to, before you calculate the mean, you have to first of all remove the product and the measurement before from after, or after from before. At least you must find the difference between the two measurements. You now calculate the mean of the difference. That is the difference between independent sample t-test and paired sample t-test. Independent sample t-test, there are two means. You are looking at the difference between the two means. While this paired sample t-test, you are looking at the mean of the difference of the two measurements, mean of the difference. So we need to understand that even when we calculate sample size also, it follows the same thing. Hugo and I was saying something yesterday, you know, when we discussed extensively for about 3 weeks, sample size determination, we talk about the pair sample also. And we talk about it also that the pair sample is looking at the mean of the difference, while the independent sample is looking at the difference between two means. Now, all these requirements for using parametric tests may not be met. If there's a violation, what will you do? When there's a violation, there are 3 steps you take. These are the 3 options, rather. There are 3 options you choose from. You may, the first one, you first of all consider, if it's possible, is to rely on the robustness of the test. That is, sometimes, if it's violated, the violation may not be so grievous. You can still use a parametric test, especially if the test is robust. For example, we give an example yesterday. We saw all those 4 conditions. The first is the most important. The first is the data set must follow normal distribution. It's the most important. The second is the homogeneity of variance. It's the second most important. The third is the interval scale. That is the type of variable you are dealing with. That third is not as important as the first 2. And the least important is the independent measurement. That is, the measurement must be taken from different people. But of course, pair sample t-test violate that because it's the same group of people you take the measurement before and after. But for independent, it's different people. So it is that one of the conditions that, which is the last condition, is that the measurement must be from separate group of people. But that one is violated in pair t-test. So we know that t-test and ANOVA, both of them do repeated measure. Anyway, t-test and ANOVA, they are robust tests because they can still be valid when not all the conditions for using parametric tests are met. So that is why we call them robust tests. And there are many. I gave an illustration yesterday using somebody's example, Dr. Yetunde Obisolu. Our work, we know this on Likert scale 1 to 5. But you cannot, when you are comparing 2 groups, you won't be able to use parametric test because that scale, after all, the values is arbitrary. It's not interval scale, it's ordinal scale. Likert scale is ordinal scale. Or when you use scale for maybe to grade moderate, severe, and severe, moderate, and mild and moderate. It's a scale, it's an interval, it's not interval scale. It's an ordinal scale. It's you that give the arbitrary value 1, 2, 3, 4. So also when we try to look at the severity of cancer, we use scale like that. But these are not the value we give them. So that is interval scale. So you cannot use, if you have something you score on interval scale, interval scale, not interval scale. That is ordinal scale. If you have something you score on ordinal scale, you cannot use parametric test. You rather go for the non-parametric. There, however, along the way, if you have many items in that scale, in the instrument you are using, you have many items, and you are able to combine them and not calculate average from it. When you calculate average from it, you can see you have introduced decimal. Whatever you get out, for example, now you have some question that is on Likert scale, about 5 of them. You now add all the 5 and now calculate average. Say this one is talking about the physical domain. In that sense, that particular average you call physical domain now, it has become a quantitative because you can take any value, any possible value. It's more like continuous variable. In that case, for that average, you can use parametric test. Now, those are the things No, Professor Wake was saying that some people see since the original thing is a likely scale, some people are still fighting. That's just the issue. You because even the test you are dealing with is a robust test. Sometimes if you have big sample size, if you run that type of thing, even on likely scale, run with chi-square, you run with the t-test, I also run with non-parametric test. You see, you give the same answer, especially when the sample size is very large. And the advantage of using parametric is that the software you are using, it helps you. It makes sense when you are interpreting it with confidence interval. It doesn't make sense when you do something with non-parametric, you are interpreting with confidence interval. You cannot even do that because it's not using the real value, it's the rank value it's using. So that is one of the major drawback of non-parametric. So these three conditions, you rely on the robustness of the test. The second one, you use a non-parametric test, which we are going to be looking at today. And the last option is to transform the data into a new set of data that are consistent with the assumption. With this last one, just academic exercise, because when you transform data, we have done it now. We have transformed data. The life is not the same again. So it's difficult to interpret. So like now, if you do logarithm transformation, natural logarithm, which is the commonest transformation people do, the mean you have with the transform data is not arithmetic, it's geometric mean. You know that in logarithm, the corresponding the counterpart of addition in the normal scale is multiplication. So what addition is in the normal scale, that's what multiplication is in logarithm. And what subtraction is what division is in logarithm. So instead of, in normal scale, the mean is adding everything together and you add everything together. But that one is geometric mean. You rather multiply, it's multiplication before division. It's not even division. When you multiply, you now find the hen root. That is logarithmic scale. So the mean you have for the logarithm scale when you transform is geometric mean. And if you now do, after you have calculated the mean, which is the geometric mean, you now, if you transform the mean back to the original scale by doing antilog, the value will not be exactly the mean of the original one. Maybe it will be closer to the median. So that is why it's quite difficult to interpret. That should be the last option or no option at all. So it's better you move in between, rely on the robustness of the test using a non-parametric test. Now, let's quickly look at you have a question?
Yes, Dr. Dolapo, I just, sorry to draw you back a little bit.
Okay.
Yes, I've had to go through somebody's proposal recently, and
okay.
When we use Likert scale, more or less like it's Likert scale, let's say you are dealing with grades of normalities of breast lump on ultrasound, for instance. Yeah. And in some of these scales, you may have one, maybe they say benign, 0, nothing, benign, but sometimes you have subdivisions. You may have 4A, 4B, or 3A, 3B, 3C before you get to 4. Now, if you have such data and you want to analyze, how do you ensure that, or how do you report that when you are looking at the statistical significance? If, let's say you are comparing two scores, for instance, before and after, there's an intervention, and then you have an after scores. So, and there are subdivisions in each. How do you really do that statistically?
Well, it depends. Some of these things, it now depends on the sample size also matter. Like now, if the sample size is large, having a sub under will make sense. But if the sample size is very small, having a sub will not make, because it's for you, the essence of the sub is for, if the sample size is large, for you to, if there are some variation in between also, for you to trash it out. Yeah. So if you have a large sample size, so if there's maybe there are 4 levels, 1, 2, 3, 4, and the 4 has A and B. You can as well make it 1, 2, 3, 4, 5. you split that one into two. Especially if
Okay, that 4 can be divided into 2.
Yeah, if the sample size is
Because
large.
I'm actually looking at the discrete nature. I mean,
What
if
is it?
you started with, no, I'm actually looking, if let's say this is a discrete data, let's say you are counting something and you cannot find an average. Are you with me? You have a discrete ordinal data. Hello?
Yes, the issue, yes. Okay, I know what you are saying now. Concerning the average I'm talking, no, the average I'm talking about,
Yeah.
it is only applicable where these different items in that scale, they come together to form a composite. You know,
Okay.
it's not, that one is not applicable to the situation you just said now. You know, some of those instruments that psychiatrists they use, all those psychometric instruments, some of those questions,
Yes.
they have many items. When they have many, about maybe up to 50 items, they now classify that as this 10 is looking at the social domain. This another 7 is looking at the spiritual domain. This another 7 look at the psychological domain. You know, all those things. So you have many items, but you can collapse the items. They have group. So in that case, when they answer the question now, the one that all those questions that are pointing at the physical health, you can add them together and divide by how many of them to get average for it. If there are 10, you can add the response together and divide by 10. By the time you calculate average, decimal has come in. Because you know those things are 1, 2, 3, 4. But by the time you calculate, you go to see 3.5, 2 point something. So decimal, by that, it has become a continuous variable, because the continuous variable in the sense that particular composite domain, not the individual item. That domain.
So if you now get 3.5 in a previously ordinal data, how do you now interpret that? Because it's something that has to do with 3.5.
In the when you now calculate the average, when you now average for the domain, you mean?
Yes. Yes. And your result is not in tandem with the original data, I mean classification. How do you now interpret that?
You see tandem with it now. You know, there are two ways people do this type of thing. In some, they will have, even when they had all these things together, they say the total score is 42 or 43.
Okay.
I understand some people do it. No, some people they will have done the validate the instrument. They will say the total score, they have a particular figure. Some they don't do that. What they do is that they calculate the average. You understand now? The total score that total score, that one may be dicey, because if you use total score, even total score is still discrete. Because if you use total score, it's discrete.
I'm actually looking at
the one that intelligent people, so what they do is that instead of saying total score, they now have all the score and divide by the number of items in that constitute what they had. You understand now?
Okay.
But with that also, the minimum will still be 1. Because you cannot go below 1. You understand now? The minimum will still be 1, and the maximum will still be 5. You cannot go above 5. Because for you to get average above 5, there must be a score that is above 5. I don't know if you understand me now. So if it is on a Likert scale of 1 to 5, the minimum will still be 1, and the maximum will still be 5. And when we talk about continuous variable, we say in between two given values, there are unlimited number of values. It doesn't say that average is unlimited. From 1 to that 5, you have unlimited, even between 1 and 2. Once it is average, it can be 1.1, 1.0, no, it can be anything. So it makes sense. You can use it. Once you calculate the average of those, it's not the original value you ascribe. So you can still use it, because the highest will not be greater than the highest for the scale. The lowest cannot be lower than the lowest for the scale.
Okay, thank you.
Now. Welcome.
Yeah, thank you.
Okay, welcome. Thank you. So let's proceed. Sometimes data set do not. I think we have talked about all this, the rationale for using non-parametric. But the non-parametric, as I've said before, does not use do not use the original data to calculate as per the way a mean. You calculate, you had everything divided, you can get your mean. It doesn't work like that, because they want you rank it. It's not the original value, so you rather use the ranking. So T-test and their non-parametric counterpart. This is an example now. The non-parametric counterpart we'll be looking at. When you want to compare a sample mean with a population mean, which is the one sample t-test we talk about, a sample mean with a population mean. So one sample t-test, if it's parametric and Wilkinson sign rank test or sign test, we are going to look at them if it is non-parametric. Compare means of two independent groups. Independent sample t-test for parametric, non-parametric, we use Wilkinson rank sum test, Mann-Whitney U test, Kendall's test, median test. This Kendall test, I will still look for it. Yeah, I know that Kendall test, I have not seen it anywhere, but that's what the list that is one of them. But in what we're going to be doing now, we'll be looking at the what do I call it? Looking at Wilkinson, ransom, Mann-Whitney, and median. Ransom, by the time you look at it closely, it is not difficult to differentiate. You will see. So it's not difficult to differentiate ransom and sign rank. As the name implies, sign. Sign means he is talking about positive or negative sign. Sign. The ransom, after ranking, you sum all the rank. So that's just the difference. So when we talk about sign rank and ransom, that's what it means. Who came? Somebody came in with Galaxy, with Nebula. So Galaxy. Somebody check it. Good evening. It's okay. So who is Galaxy?
No, it's me. It's me. Dr. Ikogo.
Okay. Okay.
Okay.
Okay. No problem. Yes. Now test the mean of the difference in peer observation. That is, before and after. Peer observation is if it is follow normal distribution. If it's parametric, is peer t-test and non-parametric. Wilkinson sign rank test and sign test. Can you see? It's the same thing that goes for non-parametric. What goes for one sample t-test is what go for peer t-test. The reason is very simple because it's only one sample. You know, if first it's only one sample of this you take. It's not two individual group. It's only one group. It's the observation you had before and after. So that is the logic. That's the logic. So that is why for the non-parametric is the same thing you use for the non-parametric. You will see how it works. Yes. Wilkinson historical background. This man, Frank Wilkinson, American chemist in the year 1945, first of all described the test. And the reason is very simple, because there are situations where the data set is skewed and you cannot use you have not made the assumption for using parametric test. So that's why intelligent people like him came up with that. And Henry Mann and Donald Whitney now built, after 2 years, published another one, built on the work of Wilkinson. We're going to see that as we calculate Wilkinson, we see the Mann-Whitney U, it's just like a step further. It's just further the Wilkinson. Then Mann-Whitney U, there are name of two people there, Henry Mann and Donald Whitney, are the one that further the work of Wilkinson, and that's why they call him Mann-Whitney U. Then popularized rather by Sidney Seger. This is the person that popularized it later in 1956. Now look at Mann and Whitney. So now comparison of one sample with a population parameter. Now let's look at the first scenario, which is the counterpart of one sample t-test. So what are the non-parametric tests under this? Sign test is a type of median test. You know that median, I say it's either sign or mood median. So sign test is a type of median test. You will see that later that this median test of is the only one that actually make use of the median. And making use of the median is not as if you use the median to calculate, you just use the median to divide the data set into two among all of them. So when people say that no parametrics, median you are comparing, actually you are not comparing any median. You are not comparing any median in non-parametric test. The only thing is that the median in those few occasions, like in the median test, the median value is now used to divide the data set. So for you to now carry out what you want to do on it. So Wilkinson sign rank test, as I said, the sign test use only directional information, while the Wilkinson test use both direction and magnitude information. You're going to see that the sign test, the one that uses median, you just use how many are above the median, how many are median below. That's all. Then Wilkinson, it's not only that. Wilkinson will be able to rank and which one, and I had those one on one side, had those one on the other side. So apart from ranking now, Wilkinson magnitude, that is the size. So we make Wilkinson to be superior to sign test. Then you're going to see that sign test is a form of median test. The only good thing about that median test, the only good thing where it is, the only way place is better than the other non-parametric is in survival analysis. Whenever there is a sensor data, that's the only one you can use among them. That's the only non-parametric test you can use for sensor data. And it's very interesting. And it's, we have already said that the median test is for comparing two or more groups. So it's both non-parametric counterpart for independent t-test and for ANOVA. That's the mood median test. No, okay, no. So sign test is just one of the median tests anyway. The Wilkinson test use both direction and magnitude. Though the Wilkinson test is more powerful statistically. Let's look at an example. One sample Wilkinson sign rank test. In a law college, a random sample of 10 students mark are noted below. Is there evidence at the 95 confidence level to suggest that the median mark is greater than 67? Step in computing Wilkinson statistic. Here we are going to compute both Wilkinson and the median sign test here. The sign test and the Wilkinson to give you. Calculate the difference. What are the steps involved? Look at the student mark 1. This shows the number of students. The 1 student, 2 students, up to 10. These are the mark. And maybe in the previous class or in another school, the median test was 67. So we want to see if this one and that one is the same. So that is why people say that you are comparing median, because what the value they gave for these other ones is the median. Is the median. Now calculate the difference. So you have to calculate difference between this and the median. So what it does mean that you want to know which one are. If you calculate the difference, now what will happen is that the one that are more than the median, when you remove the median for it, will give you positive mark. The one that are less than the median, when you remove them, it will give you negative. So it's divided into two. So ignoring the sign, rank the different smaller mark and rank equal to 1. Separate the positive. Let's just go to this straight. Look at it. Instead of just talking. It's demonstrated here. Look at the scores. The first step is to look at the difference between this and 67. When you remove 67 from all of them, this one is 4, 12, minus 27, 3, 15, 5, this. Now, if by the time you look at the value, you neglect the sign now, you neglect the sign and now rank it. When you now rank it, what you mean by ranking is that, look at it. You know they are scattered all around. Which one is the smallest? You give you 1. Number 2 is the smallest. Give you 1. The next one is 3. The value is 3. Give you 2. The next value is 4. You give you 3. Rank 3. The next value is 5. You give you rank 4. The next value is 7. You give you 5. Can you see? Forget about the rank in the sign in it. It's just the magnitude. The next value is 8. You give it rank 6. And the next value is 15. You give it rank 9. And the last value, the highest one, is 27. You give it rank 10. You know, if you consider the sign, 27 minus 27 should be the smallest. But you are not considering the sign. You are just looking at the magnitude to rank. Now, after you have done that, you now say sum all the positive and sum all the negative. The rank of the positive. So you know that the one that are negative, they are minus 27 and 7. Look at their rank, 10 and 5. Can you see? Those ones that are positive, look at their rank. All those ones, these 4, 12, 3, 15, 5, 9, 2, 3. Look at their rank, 3, 8, 2, 9. So when you add these together, the rank for the positive, you add them together, is 40. The sum of the negative rank is 15. So you now see, for Wilkinson will just tell you that, okay, the one that has the higher test statistic is 15, the smallest rank, the smallest value between the two. So this smallest value is 15, and that shows that it doesn't have anything to do with the rank it has. So irrespective of whether it's positive or negative, the smallest value of the two is the statistic. And this is an example of the Wilkinson statistical table with the degree of freedom with the n. Look at the n. For 0.05 level of significance, this middle one is what we usually use. And for sample size of 10, like the one we are doing is sample size of 10, the critical value is 8. It is when your value is less than that critical value that is significant. You know, I said it before, all statistics up to yesterday that we did, even the one we did yesterday, is the t-test. All the statistics at the increased value, the more likely it will be significant. But for Wilkinson and McNewy, the less the value, the more significant it will be. That shows that this statistic will move in the same direction with the p-value. The smaller it is, the smaller will be the p-value. That is, the smaller will be the probability that the result is due to chance. The more significant it will be. So unlike other statistics, there increases, the move in opposite direction to the p-value. So you can see that from here now, since the critical value for that degree of freedom would be, for that sample size of 10, is 8. This one we have calculated cannot be significant. Since test statistic value is greater than the critical value, hence I said we know hypothesis, so there is no significant evidence that median rank is greater than 67. So there is no significant difference. I don't know if there is any question before we go and run it. Any question?
Hello, Dr.
Yes, sir.
Dr.
Yes, sir.
Before we do that, I was just looking at your question now. And when you started, you said that when you are dealing with non-parametric tests,
yes,
the word confidence interval does not come in.
Yes.
Am I correct? Now, that question you just
I say it's difficult to, okay, go on.
that question now that is asking us to find the median difference or whatever, it was given with a confidence interval of 95%. That question, the question you just solved now. If you
Okay, yes,
go to
okay,
the
that's
question,
great.
what
That's great. Yeah.
what is the significance
Okay,
of
let me explain that. Let me explain that. Normal distribution is the basis for hypothesis testing.
Yes.
So that confidence interval we talk about there is talking of generally hypothesis testing, and it's a general language. Just like if you want to calculate your sample size, now you see that once you choose 0.05 as your level of significance, your level of confidence is 95. So what is talking in that place that you should reject no hypothesis as 0.05. But the confidence interval I talked about before is not this one. It's talking of when you estimate a particular parameter, you have your statistics, okay, the mean value is this. That mean value you get, or whatever, either median or whatever you get, is from your sample. Since you did not take the whole population, it cannot be equal to the parameter. That means that value you get is a statistic. It's not, it has a corresponding value called parameter in the population, which is the real value in the population. But what you have just gotten at the sample you have taken. So you now want to now say, okay, since I don't have access to the population, you now calculate in 95% confidence interval, you calculate in that sense is a range of value within which you can say, okay, I'm 95% sure that the real population value for this thing will be in between this and that. Do you get the picture now? So why I said that was that, in the, when you are dealing with parametric text, you calculate the mean. You use actually use the value, the data set to calculate the mean. And you calculate the mean different. When you calculate the mean, though the hypothesis test is different from confidence interval, they are two separate inferential methods. But what we are saying is that when you use parametric test, you are able to use the data set to calculate the mean value. And when you now calculate the confidence interval, if you can even use the mean to calculate the confidence interval, it is easier for you to interpret the result of your parametric test with confidence interval than the non-parametric, because non-parametric doesn't even use the value. It actually rank. When it's the rank, it now use the rank value. The rank value are different because you can have data set that are different. Imagine now you come with hemoglobin concentration data, another person come with a kilometer, maybe it's an engineer or a transporter come with distance travel, and you. So if your sample size is 150 and that person is 150, when it is ranking, you may rank the same thing. But it doesn't mean that if you are calculating in mean distance, you'll be talking of 1,500 kilometers. While you are calculating your hemoglobin concentration, you are talking of 15, 16. Can you see now? So because the rank is using, you can't feel the effect of the data much. So it's difficult to now interpret it together with confidence interval. I don't know if you have communicated now.
Yes.
Yes. So that's just
it. You made a okay.
Yes. You have a question?
Yes, sir. You made a statement. This is the second time you said it. You said it yesterday. You said something that the normal distribution curve is used for hypothesis testing.
Yeah, it's the basis. It's the basis for hypothesis testing.
Okay, the basis.
It's the basis. If you look at it, I was talking about something like that yesterday because
yes. Okay.
If you want to explain, if you remember, even when we talk about chi-square, we related it to normal distribution because the person that first described chi-square person actually square standard normal deviate to discover chi-square distribution. If it's even t-test also, the person that described it, they now discover that, look, as the degree of freedom increases, it looks more like normal distribution. Even the F-test, all of them are related to that normal distribution. So the normal distribution is easier to conceptualize, and to me, the way I see normal distribution is that many things that is hidden. Normal distribution is the one that represents them. There's all these hypothesis tests. It's normal distribution that represents that we know. Because we can easily say, oh, normally distributors are available everywhere to us. Height, weight, most of the most biological variables, most naturally occurring variables. They follow normal distribution in the sense that as the value increases, the population that have the attribute, the value increases also. Like weight now. I usually use weight because it's the easiest for you to understand. The adults now, adults that weigh 30, they are very few. But the people that weigh 35 will be more than the one that weigh 30. The one that weigh 40 will be more than the one 35. The adult that weigh 50 will be more than the one that weigh 45 or 40. Adult that weigh 60 will be more than the one that weigh 55. Adult that weigh 70 will be more than the one that weigh 60. But beyond that, around that 70, when you begin to go up, the number that weigh 80 will be less than 70. The one that weigh 90. So if you look at it, if you plot the value as it decreases along the horizontal and the number in each category along the vertical, the thing will be going up and it reaches that value around that 70, and the number of people that have it begin to go down. That's what brings that curve, the number that go up and come down. It's so funny in such a way that is one side is the mirror image of the other. Can you see now? So, and when we talk about probability, we say that probability is just the chance that when we say the probability of a variable now, of a value, it means that if you say the probability that your weight is 70 or 50, how do we get that? Unless we put that the number of people that have that 70 over the total number of people in that category. When we now say, okay, this is the probability of somebody having weight 70 among this population. Do you get the vision? So since we know that the probability cannot be greater than 1, so we know that there are two types of variables. There are some variables. They are all these categorical variables. You know all the category. You know all the possible category. I gave an example yesterday. Ethnicity, geopolitical zone. Sex is a categorical variable. As we are now, in any population, is either male or female. So we cannot count in any population, count the number of male, count the number of female, and that's okay. This is the probability. If the male, if they are 50-50, also the probability of getting a male is 50%. Female is 50%. But if the male are more than the female, maybe 30% female. And that's oh, if you count everything, now put female over total, give you 30%. That shows that the probability of getting a female in this population is 30%, 0.3. So for categorical variable, because it is possible for you to know the different category, all the different categories, you can actually have the different categories and calculate all their probabilities. But there are some variables it is not possible for you to know all the possible values. Like blood sugar. Can you tell me all the possible value of blood sugar? You cannot, so you cannot tell me. So that is why it's difficult to now have the table that will show all the possible blood sugar value and put the probability there. Do you get the picture? So that is when you are doing your research, you are doing your research, you do your research, you see that all the categorical variables, you can easily get the probability distribution. The research is show you don't know that it's probability distribution. When they say ethnicity, you say Hausa, Igbo, Yoruba, you now put the number of each category over the total. You now say is Igbo 30%, Yoruba 30%, Hausa 50%. You put it. That is what you have in your table is probability distribution. You don't know. There is a discrete probability distribution in the sense that that variable you are showing, you know all the categories. You now put their probability there. That's the meaning of probability distribution. Probability distribution is the list of all the possible values of a variable and their probabilities. So you will see that it is only categorical variable you can do that for. You cannot do it for continuous variable. If you want to do it for continuous variable, what you do now, you now range it. That is why for you to tabulate sugar, blood pressure, and age, you cannot use the original value because when you run, you just see a lot of, even the one you see there, they are not it's just the one you see. Those are not the only possible value you can get. A blood sugar of 925.2. It doesn't, you can have 25.33. So even the one you have in your data set, even if there are 1 million, your samples are 1 million, those are not it's not exhausted. Can you see now? So for quantitative variable, it is not possible to know all the possible value. What you can do, you cannot, that shows that you cannot have a table that shows the probability distribution of continuous variable. Can you see now? So what you can now do, the intelligent people, that's okay. Well, let's plot a graph. Let's just have something like a graph or something like that. Okay. That graph will say, okay, everything on that graph is the total. So the graph, the normal distribution fits that description. So when people discover that now, it opens eyes to statistics. That is why it's the basis for it. So because of the shape of the normal distribution, people, when they study it very well, now discover there are two things that they should discover in normal distribution that open that gate. The first one, they now discover that in between minus 1 and plus 1 standard deviation, 68% of people in any variable that follow normal distribution, whether blood sugar, weight, distance, think of the IQ, any variable that follow normal distribution, in between plus or minus, it has been proven over and over. In between plus or minus 1 standard deviation, 68% of the subject will have the value in between, the value that corresponds to minus 1 standard deviation and plus 1 standard deviation. And they discover that in between minus and plus 2, about 95.45%, we have the value in between plus or minus. But the researchers, they were very intelligent. They are interested in the middle 95%. They now say, okay, if the minus and plus 2 correspond with 95.45, but the middle 95, they don't want that 0.45 from me. They just want the middle 95. That shows that it won't be up to that 2 standard deviation. That is the origin of 1.96. So what corresponds with the middle 95 is the 1.96, almost 2. Can you see now? So that understanding of the way it is the first thing. The second one that made it standard is the graph, as you see, since it's bilaterally symmetrical, one side is the mirror image of the other. So if you divide it in the middle, that shows that the other one will be half, the other one will be half. Just like what I was saying yesterday, they give you bread. Forget about the size of the bread. They say go and share it equally. All you need to do is to be able to divide the bread in the middle so that I take half. So it doesn't matter what is the kilogram of the bread you take. The issue is the half. Whichever bread they give us, whatever size of the thing they give us, they say we should share equally. So if the line in the middle of the normal distribution is divided into 2 halves. So half, one will be half, the other will be half. So the area when you half plus half is 1. So the area under the graph you can say is 1. I don't know if you understand me now. And since probability cannot be greater than 1, so you now say, okay, the total is 1. So you now apply it to continuous variable that you cannot actually have a table of all the possible value. So the graph of probability distribution is called probability density function. So that is what we used to describe continuous probability distribution, because you cannot have a table of continuous probability distribution. You can have it for discrete, but you cannot have a table because you don't know all the possible values. But you can have a graph that shows that this is the total. So the area under the graph is what we'll be using now. So it's not possible for you to say what is the probability of a particular value in continuous probability distribution. It's not possible. You cannot say what is the probability that somebody has blood sugar of 61. It's not possible. Because you don't know why it is not possible. If you even gather the people in your district, you gather the people that have blood sugar 61. Then what it will be? Your denominator. How many possible values is infinity?
How many possible? Yeah.
So it's infinity. So what you now do is you can only know the probability of a range of value. You cannot know the probability. So you can say, okay, half. How many below half, below the middle, which is half, above half, in between 2 points. You can know the probability above this, below this, between these 2 points on that graph. So I think don't let us deviate. I think I explained this thing. That is why I actually say go and watch that video on probability and normal distribution. I explained this thing extensively there. So that's why I want everybody to go and watch the video. Is there any question? What I just said now before we proceed? Because that's just a digression. Because sometimes it can be confusing, but it's not confusing. When you understand, you're able to conceptualize it. It's very straightforward. Any question before we move forward? So we'll go and run this Wilkinson this.
Can you go back to the slide before this one? Because I'm seeing some of positive rank, some of negative. Okay.
The logic is there. If you remove 67 from each value, those values that are less than 67, it will give you negative mark. Those ones that are more than 67, it will give you positive mark. That's what has happened. So
the positive ones are above, Abby. Okay.
And if you remove 67 from each of the value. Any value that is less than 60, the median, which is the 7, the median they gave you is not the median of the data set, the median you are comparing it with. When you remove system from you remove from each of them, those ones that are more, that are less, will give you negative value now. Those ones that are more will give you positive value.
Of course.
Yes. So you first of all rank irrespective of the sign, whether negative or positive. You rank the value. The value. When you rank it, you know which one. The smallest is 2. This is different. The smallest is 2. You
said irrespective of the negative or the positive.
Yes, of the sign. The sign positive. You know, all this positive. We didn't just put anything you didn't put positive. Mean positive.
Oh.
Yes, now I didn't just put the positive there. When you say you are ranking something, anything you didn't put.
Oh, I see what you mean. The values are not. Yeah, I remember now. The values are not important. The minus or the plus is not. It's the number itself that is ranked.
Yes.
The lowest. I remember
all
now.
These
okay.
Things, they are positive. All these things, we didn't just put negative there. You know, you don't put. If something is plus, you put plus. You don't. You just leave it.
Yeah, we don't put it in front. Yes.
So these are plus. All this one, when you remove it, they are plus. So you have 2 that have negative here now. That one that's minus 2 somewhere, and minus. Look at this, minus 27 and minus 7. Those are the 2 that are negative here. All of them
negative,
are.
Okay.
So you first of all rank irrespective of. You know, if you want to rank in based on the sign, minus 27 should be the smallest.
Exactly.
Minus 27 should be the smallest.
The smallest, yes, but I saw that it was actually
plus 15 should be the highest. Plus 15 should be the highest. But you are ranking no irrespective of the sign. So if you rank, you first you use the magnitude. 2 is the smallest. You rank it as 1. Then the one that this way I will even come to put the sign. 3 is the next one. Rank it as 2. 4 is the next one. You rank it as 3. 5 is the next one. You mark it as 4. Then 7 is the next one. You mark it as 5. Irrespective of the sign. Then 8 is the next one. I mark it as 6. Then 9 is the next one. I mark it as 7. Then 12 is the next one. I mark it as 8. 50 is the next one, rank at 9, and the highest one is 27, rank as 10. So you now see, you now separate the rank of the positive and negative. This is the rank of those ones that are positive. This is the rank of those that are negative. Now sum it together.
Negative, I get.
That's what it's called. They call it sign rank.
Rank sum. Okay,
you know, this one is not rank sum. This is sign rank. That is when you look at the sign. You rank and now sum all those ones that have the same rank. So we sum the one that has positive rank and sum the one that has
you sum the one that has negative.
Yeah.
Okay, I know.
That has negative sign. So that is. So we now see that the positive sign they are 40. And the negative sign 15. The smallest of it is the statistic, which is 15. And the
the smallest value between 40 and 15.
Yes,
I
now.
didn't understand that part.
Look at the positive sign, 14.
Oh, out of okay, which one is the smallest? Okay.
So 15 is the smallest. Irrespective, it doesn't really
The
matter which
small.
sign is it. Yeah, it may
Oh,
be
I
positive,
see.
may be
Okay.
negative, but the smallest is the smaller of the two value will be the statistic. And the statistic,
Okay.
if we look at the statistical table, this sample size for sample, because the sample size
Okay.
were and the under 0.05 level significant, the critical value is 8. And
Okay.
this one is greater than the critical value. It has to be less than the critical value for it to be significant. I already told you that
Yes.
that's the only statistic that you work in that direction. For it to be significant,
Exactly.
it has to be small for it to be
Okay.
significant. So in that
I
case now,
remember now.
this one is not significant. It has to be less than that for it to be significant. That's just it. So that's just
Okay.
better.
Thank you.
The most important is for you to know how to run the data. So I think we can run it now. We can run it. Who has the data set? People are not prepared to. Yesterday is me that run it. You people are not prepared to work. So let me look for the data set. Let me open. Let me look for the data set where I put it. I think it's Mark, yes. Can you see now? This is the data set. Can you see?
Yes, sir. Yes, sir. We can.
Yeah. So this is data that look at the medium, and this is the mark here. Can you see? For 10 of them. So
Yes, sir.
analyze. So where do you go to? Go to non-parametric. Non-parametric test.
Legacy dialogue.
Legacy dialogue. No,
Then
you
it's
now
to
deal
bring
with
out the
one sample. It's just one sample. No, I think it's one case, one sample. So move. Well, there's another option there. It's not this one. Okay, it's on this. You know, I told you before that for the non-parametric, both the one sample t-test and the pair sample t-test, is the same procedure. So you related. I think it's this mark you remove. Can you see Wilkinson? If you want the sign now, you click on the sign test also. In one procedure, it will do it for you. Okay, I don't know what really happened. The positive, okay, that was why I changed the pattern. Let me just rerun it. Though it's the same result anyway, it doesn't change anything. I don't know if you see the, let me share the results.
So you put the median under variable 1. Then you put the mark. Was the mark under variable 2?
Well, it depends on the way. It gives you the same result, but what will happen is that if you look at the one we did, what is the sum of the positive? The sum of the positive is 14. I don't know if you understand me now. Then the sum here, the negative is
Yes, sir.
yes. Just look at the sum now. The positive is 14, the negative is 15.
Yes, sir.
The round sum. So whichever way you give you best, it will just, you know, the thing that is choosing the smallest one is the statistic. Doesn't really matter which sign. But I just want you to, because sometimes the way you put it, you know, the computer, what you put first determine which one is going to remove from the other. So you can see now.
Oh, that is true. I understand.
If you look at it now,
Okay.
Look at the p-value. It's not significant. Yeah, yes, I'm not. It's not significant.
Yeah.
But you know, this one you are seeing that is sign test. Yes, I'm not. Is this one just use Z? But this one, look at the Wilkinson hand here. Just look at it. Telling you the smallest one is this. So there's a procedure, is one complex procedure to now calculate the Z from that Wilkinson for you to get, because Wilkinson, when he describes it, just say whichever one is smallest is his statistic. You get the vision now. So there's a complex procedure for you to now transform that score into a Z. But whichever way you go to see the p-value is not significant. If let's say that smallest value is less than that 8 now for the degree of freedom for that sample size, it will be significant. I don't know if you understand now. Do you understand?
Yes, sir, I do. Thank you, sir.
So
yes,
just
sir.
for you to just know.
Yes, I do. Yes.
So any question on that? So that we'll move to the next one. Yeah, people are just silent. Okay, hope people understand.
No, sir, I'm here actually. I
No, it's only you that are
understand
talking, no problem. Let's look at we have just described how to do the sign out now, one sample test. Let's look at two sample tests now. But these two sample and pair sample, this data you have there, it works for both two sample and pair sample. Let's just look at the first aspect of it, which is the two sample T. So we have two sample here, people that took drug and people that took alcohol. So you want to see the rate of depression among people that took drug and took alcohol. So we can decide to go for Sunday data alone or Wednesday data. It doesn't really matter. It's having two data sets for you for drug. So if you look at it, this way it's enter in the SPSS anyway. It's like the way it's enter. It's in series. Participant 1 to 10 is on drug. Participant 11 to 20 is on alcohol. So this is their depression that was measured on Sunday. It can be a data set on.
I'm not seeing. I can't see.
Can anybody see?
No, your screen is not showing.
You will have talked. I thought maybe I shared the screen. Okay, sorry. Can you see it now? Can you see the screen now?
I'm trying to come on.
Yeah, I can see now.
Sorry for that. Look at this is a data set on substance use and depression. Just give me 1 minute. Just be looking at this data set. Just 1 minute. Yes, I'm back. Hello, are we there? Are we there?
Yes. Right.
Yes.
Yes,
So
right.
what can you see about the data set? What can somebody say about this data set? The BDI
It's
vaccine
about
depression in inventory. BDI, I mean vaccine depression, is a depression score. And so you want to say something, sir?
no. You have already started saying it now. What I wanted to say just about the data showing the effect of two different this thing. One is drug, the other one is alcohol.
Okay.
And you are measuring the level of depression.
Okay.
So the first measurement was taken on Sunday.
Yes.
Then the second measurement was taken on Wednesday. So it's a data of before and after.
Okay. Okay. It's two-way.
Yeah.
If you look at it, depression on Sunday and Wednesday, yes, it's before and after. But if you also look at it, the depression for drug and for alcohol is two independent group also. Can you see now?
Yes.
So, like, okay, Dr. Igilo, Ugo, is he not there? No, maybe he went to give baby food. Now, why I'm calling is that one of their colleagues that just analyzed data. The data is like this. When people do 2 group or 3 group, they say experimental and control. Before and after, that is the way the data look like. It has the component of 2 independent are in series. Look at participants on drug. There are 1 to 10. There are 10 of them. The participant on alcohol, there are 10 of them. There are 2 separate groups. So you can say drug and alcohol. If you look at it, they are entered in series. So drug is one group, alcohol is another group. For both of them also, both the drug and alcohol, they have clear data before and after. Does it make sense now?
Yes.
That's just it. Dr. Iguilo is not there, okay? Because
No, sir, I get it. I'm here.
no, I was calling you. I said you saw what Prof said. Were you here or you went to give your?
I was, but I'm here now. You were asking something, sir.
You are not serious. I said that this data set you are seeing here, that is how. I said that there are 2. You can say that there is before and after. There is independent also. If you look at the depression on Sunday, measure for all of them, and on Saturday, measure for all of them. That is the example of before and after paired. Sunday, Wednesday rather. Sunday, Wednesday.
Yes.
That's paired. That's one aspect. That's one aspect. The other aspect also, we also have the independent group because we have the drug and the alcohol. I don't know if you understand me now. So that is how your friend's work, this Dr. Emina's work is.
I understand.
He has Tejosho, Oshodi, and Ikotun, 3 independent groups. And also have before and after, pre and post. Can you see? So you see the data set that you have
for each of them.
Control, pre and pro. Yes. You see a data set like that.
Oh my goodness, I now understand.
Independent as 2 groups or 3 groups that are independent. Wow. You enter it in series. Can you see drug from 1 to 10? The alcohol from 11 to 20. Then you now have the score on
1 to 10. Then there'll be another one. Let's say maybe another thing, so, 1 to 10.
Yeah, that is people that do experimental, they have pre and post. That is the type of thing they have. They will have the experimental group, they have control group, they have pre and post. So in that case now you have 4 sets of data in the same place. Yes, I mean now. So
exactly.
You have drug pre, drug post, alcohol pre, alcohol post. So if you want to analyze both pre and post.
Alcohol pre, alcohol post.
Yes. If you want to analyze.
Sorry, sir. My hand is up, sir. Before you take that next comment, sir.
Okay, yes, sorry.
Okay, so now assuming the parameters you are measuring for this drug and alcohol is more than just one parameter, are you still going to arrange them in this order?
Yes, yeah, you can what you can do is that if there are 5, if there are maybe 10 variables you are measuring.
All right,
are you listening to me? You may decide to first of all put all the pre from 1 to 10, all the pre. After you are finished, you now enter post from 1 to 10 also. Or you may decide, this lady that sent her work to me, the rubbish thing she did was that each of the variables you put pre and post. Pre and post. There's me, I don't like that one. You are supposed to, all those variables that are pre, you put the pre and put pre in there. You have to indicate that they are pre, because it's the same thing you are going to do for the post. So you are still raising hand. Jane, are you still raising hand?
Okay. So yes, sir. So just like we have Sunday here and Wednesday here. Yes. So for every single variable that we are measuring,
that you measure pre and post, you have to put
at the end of each variable. I put pre, and so that you will know that this one is pre, and then the other one is for post.
Exactly. Because for each person you have pre and post. So I've already told you one line when you are entering your data, one row is for one person. If you do pre and post, everything should be on that row. So if you take measurement 3 times from that person, all of them should be, you may say, 1, 2, 3.
So Lisa, just to learn, what was her error? What error did she now do?
What's that? No.
What error? What did she do? So to learn.
No,
in terms of arranging the data.
Actually, she didn't arrange it now. She did. What really happened is that when she sent the data to me, she sent in a separate Excel file for all of them, separate Excel file. And I say, and I wanted to now put it in what do I call it, in one Excel, so that I can now read it in SPSS and clean it. And I've discovered that the way you even put it on separate, it's not the same. You know, if you are say as location and maybe column X now, what the variable you put in column F for HOD is different from what you put in column F for Tejosho. Can you see? So in that case, you cannot merge.
Okay.
So I have to now ask her to go and merge it first in an Excel and send it to me. Because it's our work, all is just most of their work are even open-ended, no rubbish work. You know, I used a whole day to be cleaning.
I don't understand.
I couldn't finish cleaning. I have to start analyzing and be cleaning. You know, I even regret taking her, even helping herself. I'm telling you, I regret helping her. I've taken it. So, this is the person that said that I already started analyzing it. I don't know what type of analysis is doing with it. Okay, let's proceed. I just want you to have a picture of the way it comes. When people say they are doing pre and post, and they have more than one group. They can even have two experimental group and one control group, just like the way the lady had. So in that case, all the just like if we have drug, alcohol, and we have cigarettes. Drug, alcohol, cigarette. if there are 3 groups, we arrange them serially. If we have another cigarette now, it will be from 21 to 30. So if those drug alcohol cigarette, they are independent group. We can look for their. So when we want to analyze Sunday now, we look Sunday, the pressure on Sunday, we compare among these two groups. Then the pressure on Wednesday among these 2 groups. So there are 2 variables here now. If you want to do independent T. So in independent comparison, what we are going to do, the first one we want to do now, we first of all do the independent before we go to the pair. So if you want to do it, and that shows that we're going to compare drug and alcohol, we do it for Sunday, we do it for Wednesday. They are 2 separate. Sunday and Wednesday, 2 is a variable. The pressure on Wednesday is a separate variable. So let's look at. So I think I've explained all this instead of reading through. Let me just explain all this. Yeah. Now, rank the depression score. So you see the score now, and I put Wednesday. Can you see? Look at Wednesday up, Saturday, Sunday down. They are 2 separate. And for each of them, I have if you look at this side, you see the way I rank it. The one that are alcohol, I put A. The one that are drug, I put the drug. Can you see? Are you following? So if you look at Wednesday, I put the score here, arrange them according to how I arrange them in ascending order. 3, 5, 6, 7, 8, like this, up to 39. The same thing I did for Saturday, Sunday. So, no, I started from 13, the smallest, up to 35 here. Now, I've arranged it. I mingle all the 2 groups together, and I arrange it in ascending order. But, however, each of them is still, I see indicate the group they belong by, say A for alcohol, D for drug. Can you see? Now, when you arrange it in this way, sometimes you may not arrange it if you can rank it without arranging, but it is easier if you want to use R to do it like this. So if you first of all give a potential rank. Potential rank is that is according to the way you arrange them, you just give 1 to 20. Because if there are 20, the rank is going to be 1 to 20. If there are 50, the rank is going to be 1 to 50. That is just it. But the first rank you give is potential rank. You know, some of them, they have equal value. Look at it now. You have 6. So in your potential rank, why will you give one 3 and give another one 4? Both of them are 6. If you look at 35, look at 30. 35 is the same. 35, 3 of them. So how will you rank one 16, another one 17, another one 18? It's the same thing if you come to the Sunday, you have 30, 13. You have 15, 15, 15. You have 60, 60, 60, 16. You know, when you just give them numbering up to the something, you discover the people that have the same value, they are having different rank. So you now do the actual rank. How do you do the actual rank? All those ones that tie, you now add together and calculate the average. You know, the 6 now for this one, and this 6, the tie. So what you do, the rank is 3 and 4. You now 3 plus 4, 7 divided by 2, because there are 2 of them, you give 3.5. So you now give each of them 3.5, 3.5. They divide it equally. If you come to 35 now, the potential rank is 16, 17, 18. When you add it together, divide by 3, it gives you 17. So you give all of them 17, 17, 17. The same thing you do for the Sunday here. These 13, 13, that are the same. You now add 1 and 2 together, I give you, divide by 2, 1.5. You give each other 1.5. Look at this 15 now. There are 3 places. You add 5, 4, and divide by 3, it give you 5. Now give all of them 5. The same thing, look at 16. 4 of them. You now add this 7 to 10 together and divide by 4, it give you 8.5. You give all of them 8.5. The same thing with 18 here. There are 3 of them. You write 12, 13, 14, divide by 3, give you 13, give all of them 13. The same thing with 19, 19 here. So the average of the 2 is 50.5. The same thing with 20, 20 here. The average of 2 is 70.5. That is how you do the actual round. Are we together? People are not okay.
Yes, sir. Yes,
now,
sir. Yes, sir.
After you rank, now all you need to do, okay, you know you have already noted which one is alcohol, which one is drug for each of them. So now this actual rank now, select the one, count the one for alcohol and add it together. If you count it now, the one that has the act for alcohol is going to be, if you add it, it's going to be 151. The one that are for drug, if you add it, it's going to be 59. That's for Wednesday. You know, it's separate from Sunday. Sunday's own, if you do it the same way, you add the alcohol together, you add the drug together, rather, it give you, sorry, the drug together, it give you 119.5. The alcohol together give you 19.5. So the Wilkinson, that was actually rank sum. After you rank, you sum for it. That's all. The one that has the smallest, what is the smallest value here for each of them? Or the small, the one that have the highest rank here, rather. What's the one that has the highest rank here? Can you see?
That would be 50.
151 drug, 150. It doesn't really matter whether drug or but the value, the one that has the highest 151 and 119.5.
Okay, the value.
Okay, that's the sum of rank is what we are we are looking at.
Yes,
okay.
Sum of rank. So the the smallest rank now, the one that has 5.9, 90.5, those are the smallest. So for the Wilkinson, those are the statistics for Wilkinson. Yes, now 90.5 and 59.
So for the Wilkinson, sir, is the smallest, Tabi?
Yes. We have already done it before.
Largest. Okay.
It's not the largest. You can see in the 59.
We have actually.
Yeah, and 90.5 for Sunday. Now, the man Whitney, you know, I said that the one Whitney take the work further. From there now, you will say that, okay, this is statistic for 59 is for Wednesday and 90.5 is for Sunday. The man Whitney now go further. Are we together? What man Whitney does is now work on all the, you now use formula. Wilkinson does not use formula. He just says the smallest. So look at the formula man Whitney now use. When you use this formula now put in, you want to have you now put in the highest rank. Yeah, it's not using the smallest rank now. The highest rank I'm feeding in this formula. Where R is the highest sum rank. When you do it, it gives you 35.5 for Sunday and 4 for. Let's run it now.
Okay, sorry, I did class. They teach us mathematics. Thank you. Oh my goodness.
I'll mute her, mother, making noise.
Okay.
No, instead of you.
Go back to the formula, sir.
Okay.
Oh,
I'll go back.
Sorry, sir. Sorry, sir.
Why you make? If sorry, you want to talk, you are supposed to mute yourself.
Sorry, sir. Sorry.
Look at it.
Okay. So, what's the definition of this one?
And it's there now. Okay, hen.
Small letter N.
N, yes. If you look at the sample size, can you see?
Okay.
N. If you look at the way they substitute, each of them is 10, 10. N,
okay.
N plus N into N plus 1. N is 10, 10 for each of them. Yes, I'm now. If you look at it, that's why you see.
Okay, so that also okay. So is the capital letter, is that one the capital N1, N1, N11?
Yeah, it's just the same thing. Yeah, it's N also. N1, And if you look at it, this N1, that is the N1 here is the highest, the sample that have the highest rank. Yes, I'm not. So each of them happen to have equal samples at 10, 10 now. N1, N2.
Okay.
The N1 into N1 plus 1, that's the one that has minus R1, which is the one that have the highest rank. Yes, I mean now. The one that have the highest rank. So we now put in here. So you see, if you look at 10 times 10 plus 10 into 10 plus 1, which is will be 11 over 2 minus that highest rank there. You now make it 35.5 for Sunday. You know, this man Whitney for Sunday now is 35.5. Whereas Wilkinson for Sunday is 90.5. Can you see? Can you see? Because that is the smallest rank. Then man Whitney for Wednesday is 4. Wilkinson for Wednesday is 59. Do you get the picture now?
Yes.
Yes, I'm not. From here now, you know that it is more likely to be significant on Wednesday because the smaller the value, you know that in this statistic, the smaller the value, the more likely it's going to be significant. I don't know if you understand me now. So from what you have seen now, you see that the difference between the two is likely. You know, we are doing two separate things now. We are comparing the drug and alcohol on Wednesday. We are comparing drug and alcohol on Sunday. They are two separate things. So maybe let's run it so that you can see it. I think who has the data so that you can go and run it? Who has the data? You're not answering. Okay.
Sorry, sir. I apologize. I'm actually driving.
What's that? What did you say? What did you say? What did you say?
Sorry, sir. No, I was saying that I'm driving.
You are driving. Please don't,
Hello?
don't drive out. You are driving. So please don't.
I'm driving, and because you're asking about who has the data.
Don't worry. If you are driving, just focus on driving. Let me go and read it.
Okay. I'll be back.
Vexing depression. No. So you can see the data now. Okay.
Okay.
Let me share it.
That's not come up.
Yes, look at it. Can you see?
Yes.
Yeah, can you see? That's the data set.
Okay.
So analyze non-parametric legacy dialogue, 2 independent samples. We want to first of all do the one we just did now, ransom.
Okay, sorry, sir. Before you run,
Go on.
can you go to the variable view?
Variable view.
Yes, sir.
That's the variable view.
Okay.
Substance is a drug, either drug, can you see, or alcohol. Then
okay, that's fine. I've seen what I'm looking for, sir.
Depression score. Depression inventory, depression score is quantitative. This one, depression, you know, this for Sunday, this for Wednesday. Once you see that when it is paired in your variable view, it's going to be 2. Both pre and post will be separate variable. Can you see now? Pre, you have to create a separate variable pre and post. Yes, I mean now.
Yeah.
But if it is independent, it's the same variable. You just arrange it in series. Like look at the the drug now, either you are the substance, either because the substance is independent, either is separate group, drug or alcohol. Can you see? This is if I show you the label now, drug was enter 1 to 10, alcohol 11 to 20. Can you see now? Because there are two independent groups, so I enter in series. But the one you do Saturday and Sunday, there are two different variables. That's why it's in parallel. So in variable view now, you see anything that is in series, will be only one variable you create for it here. Is when you are entering, you enter in series. But the other one is two variables. That's why you enter them in parallel, because it's two separate variables, pre and post. Does it make sense?
Okay.
Analyze. Parametric. Two independent samples. So this is the, we want to run the two. We can decide to run only one first. Maybe we should run only one first so that it doesn't confuse people. Let's run.
Okay.
Let's run one by one. So 1 and 2. No, you enter, you coded drug 1, then alcohol 2. Can you see my Whitney? Can you see? This is Sunday. Can you see? This is the depression of Sunday we run now. Welcome.
Okay, you have to share the output screen.
Okay, sorry. I didn't know. So you can see it now. Can you see it?
Yes, sir.
So you can see the can you see the rank? Can you this is ransom 119.5. Then for drug is 119. The alcohol. It doesn't really matter which one, either alcohol, but there is a smaller one that is statistic, which is 90.5. Can you see? That's why it come here now. You can see Wilkinson. You see Wilkinson statistic now, 90.5.
Yes, I saw a message.
Who is making noise? So you will see the smaller one is the statistic. Can you see now? Is the Wilkinson statistic? Can you see here now? 90.5 under the statistic now. 19.5. That is the sum for the alcohol. It's not because it's alcohol, because it's the smaller one. That's one. Look at the man Whitney calculated 31, 35.5. That's the manufacturing statistic. So if you look at it, Wilkinson first before man Whitney is a step further. Man Whitney U is a step further. After you have summed the rank, the Whitney go further to calculate this. So whichever way, both of them have the same p-value. So to transform this Wilkinson or man Whitney U statistic into Z is another complex this, but just know that look at the p-value 0.269. It's not significant. You know that even if you go and check the Wilkinson statistic on that something for a sample size of 10, you know that it cannot be, though there are two now, even for samples of 20, because there are two of them now. For samples of 20, if you look at it, this value is very high. It has to be low for it to be significant. So let's run the one for any question before I go on?
Yes, there's a question.
Okay, sir. Okay, sir.
When you were running, did you click Man Whitney U and Wilkinson separate, or the moment you click one,
No.
the two of them will come automatic?
Okay, let's go back there now so that you see. Let's just go back there. When you see two independent, can you see? It's just only one man witnessing you that is showing there. But with Christian, we don't, because it makes sense like that, because man witnessing you is a further test. So if you look at our calculation, before you can calculate man witnessing you will have calculated me with Kingston first. So if it's showing man witnessing you, with Kingston is a step. Before you, just like before you can have your PhD, you must be a graduate. There's only in the exceptional cases. If somebody is a junior, they just speak, they say you're a professor. Somebody may not have PhD before you become professor, but it's a rare occasion. He believes that there is a step before the other. So that is man witnessing you is a step further. That's why they show man witnessing you here. Before you can calculate, so this will come. If you now look at it now, it shows both statistics there in the output. So let's do for where's J now? So the Wednesday one, can you see? Can you see? Look at the Wednesday on. If you look at it, the 59 is the Wikisi statistic here. Look at it here, 59. And man with new is 4. It's very small. So you can be sure that it's going to be lower than the critical value. So that's why it's significant. You see 0.00. So the p-value is extremely small, less than 0.001. Are we together? Any question?
Yes.
What's the question? What's the question?
I didn't say there's question. I said yes.
Okay, we are together. Okay, that's great. That's great. So let's move further. The last one now will now be, okay, let's now consider, it's not even the last one anyway. Let's now move further. We have just done the, the data set I presented, we have just done independent aspect of it. So we have just done Wikisi ransom test. And with me, let's now, this is the output just show now. Let's now go to Wikisi.
I wanted to ask, the data you just ran, it was just for one of them.
It's for both.
It was just for one of them.
One of them as by what? No,
because I remember you putting only one. You said let's this one first in your when you were running the analysis.
I just run on Sunday and now run Wednesday. So
okay, I ran the other one. Okay.
But yes, I don't want you to confuse people because it's like 2 data sets. People usually confuse. So you can decide to just like when you want to do mean this thing, systolic and diastolic. You move in both systolic and diastolic at the same time. You get the picture. So is they are separate variable. So that
okay, sir. Thank you.
They're separate variable. Okay. Let's look at Wikisi rank sum now. No, we have just talked about rank sum. Let's talk about sign rank. Wikisi sign rank. Now, don't let us waste time on talk. Look at the same data sets now. What we now did now, that Wednesday here, that Sunday and Wednesday. The first column blue is Sunday. The second column, this one is Wednesday. And we have, of course, we have for drug and alcohol. So, look at the other one. We compared drug and alcohol. We did separately for Wednesday and Sunday. Then in this one now, you want to do for drug, you want to compare Wednesday and Sunday. You're going to do separately for drug, you do separately for alcohol. Can you see the difference? The logic. So you want to compare Wednesday and Sunday data for drug separately, for alcohol separately. Now, this one we are looking at the difference because it's paired. We are looking at pair. We are looking at it as a paired group of data. Now, you remove one from the other. Let's remove Sunday. If you remove Sunday from Wednesday, what you can see now is like the score on Wednesday are higher. Somehow. It doesn't really matter if you remove first. If you remove this from this, it will give you 50 from 28, give you 13. 35 from 35 0. So if you remove this Sunday from Wednesday, it gives you the difference. The same thing goes for the alcohol also. We remove Sunday from Wednesday. These are the difference. Now, the difference now, of course, some will be positive, some will be negative. Like this, if the value are the same, it will give you 0. And anyone that gives you 0 is out of the calculation. And you see, if you look at exclude, because it doesn't have sign. Anything that is 0 doesn't have sign. If something is above 0, it's positive sign. Below 0, negative sign. Anything at 0 has no sign. So, you know, it's sign rank. Sign rank. So, anyone that Sunday and Wednesday are the same, like 27 here, the difference will be 0. It's out of the game. So you now, after you have done the difference, you now give it sign. The one that are positive, you give positive sign. You want, like for the drug now, all of them are positive. But for the alcohols, it's only one that is positive. Almost all of them are negative. Can you see? Now, you now rank the value irrespective of the sign. You look at the magnitude. Look at it. The smallest here, apart from the 0 which is excluded, the smallest here is 6. That's why you rank 1. Now, the one that is next will be 13, because there are 2 of them. We jump a step. The step is to say, okay, we give potential rank instead of wasting time. You know that both of them, one will have been 2, the other one will have been 3. So when you add 2 to 3, divide by 2, give it 2.5. That's why each of them 2.5, 2.5. The next one will be 32, and there are 2 of them, or is it 2 or yes? I say 32, 15 rather. There are, look at it, 15. So 15, instead of giving 4 and 5, you know, you now had the 4 and 5 divided, making 4, 5, 4.5, 4.5. That's the way you do the ranking. So you do the same thing for this. Now, you now separate the positive rank on a column and separate the negative rank. Of course, for this one, all of them are positive. That's why the total for the positive is 36. For negative is 0. No one is negative. For here, it's only one that is positive, and that is the 8. The rank is 8, and the other one that all those other ones are negative. You add them, make it 47. So the positive rank for drug is 36, 0 for negative. For alcohol, the positive is 8, 0 is 47. As you know, the smaller rank is the Wilkinson. The smaller value rather is the Wilkinson. Look at it. For drug, total positive 36, total negative 0. Alcohol, total positive 8, negative 47. The test statistic is the smaller of the 2, 0 for drug and 8 for alcohol. You know. So let's run it. So let's run it now. So this is not the data set. The pressure. Okay, this the same. You know, it's the same data set we use for that one.
I'm actually struggling to see your screen.
Okay, go on.
Dr. Lapo.
Yes, sir.
I'm struggling to see your screen.
And you cannot see? Let me reshare.
I can't see your screen, the one you are sharing. Yes.
Have you seen it now? Is the SPSS screen, the data set? I want to run this.
No.
Okay, don't worry. Let me.
I know.
Let me stop sharing then and share again, because sometimes. Can you see it now?
I think it's my internet.
Can any other
internet connection has some issues.
Other people, can you see it?
Yeah.
I can see.
Okay.
We can see.
So you know, it's the same data set we use for the rank sum. This China. So it's just the when you go to non-parametric. Now, if we're talking, okay, something you have to do here, since it's together, you know, separately for drug and separately, before you now do it now, since they are together, you have to go and split it. So I go to data. You know, when we're doing SPSS, we talk about splitting data. You go to data, you now click on split, and it's a split file. So you now click on compare group, and now split by the substance, that's the group data, the group variable. Now put it there. So that it's going to run the analysis separately for drug and alcohol. Otherwise, it will run it together. So when you split it, you now go to, okay, let me, because the thing is now, let me reshare it. So I've split it. So I'll now say analyze, non-parametric, legacy dialog. This one now, two related sample, just like what you did for the other one. Just move them in. So PC is already there. Just click OK. Let me share the output. Yes. Can you see now? Can you see the output? You will see the total sum of round for negative is 0 for drug. Sum of round for positive is 36. That's what we calculated. Then for alcohol, sum of round for negative 47, positive is 8. Of course, the smallest value, the smaller value rather, is the Wilkinson. So if you go down, you see the drug, so it's not showing the, anyway, is just showing the Z. But you can see from what you see now, you know that both of them are, look at, they are very small. Of course, which one will be most significant? Drug, because the value is 0 compared with 8. The smallest value is 0 in drug compared with 8 in alcohol. That's why look at the p-value. It's more significant with drug. It's 0.012 compared with alcohol, though both of them are significant. So any question?
The interpretation of the significance is the problem I have here.
Is that one?
How can something you are comparing now have two significance?
Okay, you have missed the one track. There's nothing.
You mean the splitting? No, I know that it has been split.
You know there are two now.
It has been split, but you know that you are comparing the two now. So
no, you are not comparing the two. You are comparing Wednesday and Sunday. You are comparing Wednesday and Sunday for drug, Wednesday and Sunday for, okay, maybe I should do something now. You know what I will do?
Are you not comparing whether okay, what you are comparing, that whether one is more significant than the other or what?
No, okay. What I will do now, let me do something now. What I will do now, just wait. I will go and select only drug and run drug alone. And how to do it, let me see, show you. Data, I say select cases, click on this, and now say substance. I will now click, because drug is coded 1. I say drug, yes, it's got to 1. So let me repeat the analysis now. If I do the analysis now, it's only the drug that will bring out the sulfur drug, because only drug I want to, instead of you split, but if I split, you want the 2. So only drug. So let's do it now. Can you see it has already canceled out alcohol? So only drug, let's run it now. Sorry. two related samples. Just say, okay. Can you see? Okay, let me share the results. Can you see, sir? Can you see it's only one paper?
Not yet. Not yet.
Eh?
Okay, I can see now.
So what you did now is you compare depression before and after, that is Wednesday and Sunday, for a group of people that take drug. That's all. So you can see what is trying to, is there any significant difference in the depression between Wednesday and, so if you look at it, you can see that the rank, which one do you remove from which? And at the end of the day, the positive rank are more. So it points to the fact that you remove Sunday from Wednesday. You know that even from the result, you know that Wednesday is higher. So the scores on Wednesday are higher. So you want to see, is this significantly higher? It's significantly higher. So there's a significant difference in the score, depression score.
Okay, so
yes.
So what you are comparing is whether the significant level of one is higher than that of the other.
Whether the score on one day is higher than the other day. And from the result you see from the data, the score on Wednesday is higher. But you want to see if it's significantly higher. What you are seeing,
okay.
Yes, that's it. You want to see, because this, on Sunday, maybe after they will have gone to church, their level of depression has gone down on Sunday. So, Dr. Balogun, you say something.
Yes, I wanted to say something now.
Okay.
When you compare to, like what Dr. Ikubu is trying to say, the two of them are statistically significant.
Yes.
But you want to know which one is higher than the other one in terms of relative.
Now, from even the result, it just happened that we combine two of these things. It may be, maybe I just want to know among some people that are taking drugs, I want to see their depression Wednesday and Thursday. You may not even have information about alcohol. But in a situation that you have the information, both of that together, you can see that the significance in the alcohol, in the drug, is higher than that of alcohol. Because if you look at the value, for drug, I'm telling you that for drug, what do you say?
Can you just interpret, if you have two p-values, one being higher than the other, can you just come to a conclusion that because this one has maybe a lower p-value, it's more statistically significant? Let's say significance in this sense means a measure of severity of the situation. Will it make a statistical sense to say, because the p-value of A is lower than that of B, then A is more severe in terms of trying to quantify the outcome than B?
Well, it's easy to think like that, but one is not encouraged to do that because the p-value is just probability.
Exactly. What I'm thinking now is that if you
unless you go and do what you call, you remember when we did odd ratio, measures of association. That is what quantify association. So with p-value, you cannot do that because it's just a probability.
Yeah, thank you, sir.
But if you are doing odd ratio, you are looking at odds of developing in this exposed, not exposed. We are comparing meals. Now, if you have two odd ratios with their confidence intervals, can you use that figure and say the odd ratio of this is higher than this?
Yes.
My thinking is that if you run a one-tail test, if you run a one-tail hypothesis on the two values, is it likely you will be able to make a more reasonable conclusion from the output you get?
Well, if you want to really do that, there's another dimension to it. If you remember, we also compare drug and alcohol.
Yeah.
So what the solution to this problem is what we discussed, was it yesterday, when we talked about different in different. Yes, I'm not. There's got something they call different in different. So if we want to know now, what we can do is that the difference we got between Wednesday and Thursday, and Wednesday and Sunday for alcohol. We now remove it.
Yeah.
We now look.
Thank you.
We now remove it from the different we got on Wednesday. I don't know if you understand me now. Yes. The really show that if there is this statistical significant difference, they will not say. So we actually even do that with let me do something. Let me do something now.
Okay.
To calculate that difference, because that's what I did for somebody. I just went to ANOVA, and now let me do the same thing. Let me deselect now. Yes. Analyze. Let me share. I want to, yes, what I want to do now, even though there are two groups, so analyze. What do we do from compare means? Okay, sorry. Is it okay? For me to do that, I have to first of all calculate the difference. How
I thought we're using non-parametric.
I want to. You cannot see. What do you say? What I want to do now, you know that the computer is when you are using hand to compute that you try to calculate the difference between Wednesday and Thursday. But in the computer, they are programming. Okay. But for us to do that thing, I want to do now that Dr. Balogun is asking for, I have to first of all do something. I will say transform. I want to compute the difference between Wednesday and Sunday. Yes, I'm not. And that's a difference.
Oh, I see. Okay,
yes, let me put the difference between Wednesday and Sunday. So the difference now will now be which one is Wednesday? University of Wednesday is like is bigger. Minus, can you see now? So I've created a variable now. If I show you, you will see.
Oh, okay.
I've created a new variable. Look at it. Different. Can you see now? Can you see the new variable that look at the difference?
Yes, sir.
Yeah. So look at the new variable that is different. So now that new variable now, when I say analyze, compare means I want to compare the difference between the two. The difference. That is the difference in difference. Now I want to use ANOVA, even though it's two groups. I want to use ANOVA. This is different. Then factor will be this one. Post hoc. That's what I want to do. Let me choose LSD. We may not run it because it's not. There are fewer than two groups for the.
Yes, that's what I was about to say.
Yes,
but I thought ANOVA was for more than.
No, I just want to see if, let's say, I just want to see. Don't worry. There is always a way to maneuver to do something. If let's say there are three groups now, then I can swear. Don't worry. I can swear created. Don't worry. I can swear created the third group. You see what I'll do now. I've created the third group now, tobacco. Because,
okay.
And because I didn't just me just put chili. Don't worry. Because this view is the one that is disturbing. So mine is tobacco. My third group. I just repeat that alcohol there. That tobacco. So what I call tobacco. So let me go back to what I wanted to do. That is, didn't want to do for me. Say somebody that doesn't have hands should not be wiser than you. So where am I? Am I like compare group means? Yes, I think I've shown you. For dependent variable, okay, draw. No. Okay. Maybe what even happened? Sorry, there's something. I think what even happened was the variable I put there. Yes, now is the difference now. Dependent list. I was not watching. There's something that is not running for me. So what I do, okay, maybe what I do, let me just share. I think that I even have the data set of that lady open. Okay, I close it. Let me open a data set. What I did. Let me just open a data set. Yes. So look at the other set. So I created, there is a variable, the difference in the percentage score among the three groups, different in knowledge change, the new knowledge change. Yes, I mean now. So what I did, you know, this new in this knowledge change is pre and post, the difference in the pre and post score, and there are three groups here. So I want to see which one have better change. Yes, I'm not the best if the change in the three group, if they are different. So what I did was just say analyze, compare means, one way and over. Sorry, compare mean one way and over. So that variable new knowledge change. The factor is a group variable. Now talk about post hoc. Yeah. Let me share the result. Can you see the result now? Can everybody see? Are you people there?
We can see, we can see.
You will see, because this person has three groups. We have Tejosho, Oshodi, and Ikotu. What it does, this one does is that the change pre and post, just like the example, the difference between Wednesday and Sunday now. We want to compare it between three groups. So what it does that this one, the I is the each group. J is each group also. You remove it from I. Mean I minus J, that Tejo show minus Oshodi. This is the difference. Of course, you know that it will repeat. If you remember when you did ANOVA, we know that it will repeat itself because because computer garbage in, garbage out. So that's the way to get the best out of the computer. It's three things you are looking for different in three: Tejocho and Oshoji. Tejocho and Ikotun, Oshodi and Ikotun. But it will give you three results. Each of them will just be repeating itself. Look at it. This Tejocho Oshodi, the difference between them 7.95 is the same thing as Tejocho. But here is negative. It shows that Tejocho is higher than Oshodi because here you remove Oshodi from Tejocho, here you remove Tejocho from Oshodi. If you remove Tejocho for a given negative, it means that Tejocho is bigger. So here you remove Oshodi from Tejocho and it gives you positive. Tejocho is bigger. And you see? So if you look at Tejocho and Ikotun also, the difference is 35. And Ikotun and Tejocho minus 35, you see. Can you see? So if you now look at Oshodi and Tejocho, no, the Oshodi and Ikotun, the difference is 27 points. So it shows that Oshodi is bigger than Ikotun. So it's quantifying it and give you the p-value and also give you the confidence interval of the difference. That is how to answer the question. Dr. Balogun. Dr. Balogun. He's not there.
Okay, so under your p-value now, sir.
Okay.
Hello. I was calling you. I'm
Hello?
listening, Jane. Yes. One after the other.
Okay, if you can display your output.
Okay, say the network is slow. Okay, Jane, talk.
Display your output, sir.
Okay.
Okay, display your output, sir.
I've done that. Look at the output.
I'm back, sir.
Go on.
Okay, so it means that this under the p-value where we have 0.001, that one is significant, Abi?
All of them, all of them are significant, sir.
Okay.
They also give
what you mean by it shows you where the difference.
Yeah, I'm listening.
Now, when it is only two groups and you are finding the difference, the difference of the difference,
yeah,
it makes sense to treat that difference as another variable and compare other ones with it.
I can't hear you. Your this is breaking.
When you have two groups, you know here that we have three groups.
Yeah. Yes, actually, the
other one
yes, actually, no problem. We can even, to be sincere with you, even the difference, we can even go and use as a calculate the difference now. I can actually go and use t-test to find out the difference. Instead of me coming, I just what just came to my mind was this what I did for this lady, because when she was talking of the
what is now the role of the defense side?
The role of the t-test. No, you are looking at the difference. You say that you want to compare the difference in drug between Sunday and Wednesday, and the difference in drug between in alcohol between Sunday and Wednesday in their depression. You want to know which one is bigger. So that is, if you can do t-test to compare the two, yeah, you will find if the one is bigger than the other. You'll be able to see. I don't know if you understand me now. Or even what at the best, if you don't do t-test, what you may do, you may still go and do the Wilkinson ransom test independent for the difference. Okay, let's even do that now. Just wait. Let's do that. Instead of even bothering myself. But I was wondering why that thing didn't work. But instead of bothering myself about that, let me go back. Let's go back to the data set, the one we are using. Our own, the vaccine depression, yes. No, I was able to this difference. I was wondering, okay, well, I put different, I don't know why. drug. I was wondering why the thing didn't work. Well, I'm coming. Just 1 minute. Why the thing didn't work? Analyze. Before I delete it, I want to see. Easier. Okay, let me just forget about that one. Let me do what I want to. Yes, let me remove this third. Yes. Now, the difference now, we can actually run that Wilkinson rank sum test on the difference we have calculated to get the difference in difference now. So now 2 independent samples. So what we are moving now here is the difference. Now within it cannot be performed on empty groups. Empty groups. See, there are some empty. Wait. What I did I wait to the selection I made.
The new group you created. No, the new group you created, group 3. There are empty cells there.
Okay.
It's not even there.
Okay.
Okay, it's been deleted.
No, okay, I have to go and let me go and remove that group. Yeah. Let me remove the group.
I used to think the man with me, he was prepared. Okay, it's the group you are looking at. It's the group that.
Don't worry. Why is he bringing me Friday? It's what? No, I open Bexing. Let me close this Friday then. Okay. Let me remove that 3 from it. Because I've already. Okay. I'll remove it. Let me try it now. Two related, 2 independent samples. Okay. Empty groups. Just leave it. Still telling me that. But that's how to. No, I've demonstrated that thing with. Let me just close all this. Where is the Sunday difference? to be able to compare these two groups. Okay, I will look at that later. Let's just proceed so that one will not disturb us, delay us. We are supposed to have close. Okay, I've seen what happened. Let's just continue. So, any question on those one we have done, so that we just go to the last one. The last one is some median tests. Go on.
Hello.
Yes.
Where you get your output from? Let's say, is it because of my with the they usually put effect size. I think it's my with you.
They usually what?
In what situations do you usually effect size? If something is statistically significant, sometimes you see the right effect size and put a figure there.
Yes, you know, that one also is another. That one is a dicey thing, because for it's not only even for chi-square, for all the statistics, you know, they try to mimic, you know, this odd ratio issue is to quantify association. Each of the statistics, people believe that, you know, because people criticize hypothesis p-value a lot, and that is why in medical literature they don't want to take it from you. They prefer something like a odd ratio, then difference between mean and confidence interval. So many people now come with some calculation from even for t for chi-square, you can calculate effect size. For t, you can calculate all the statistics. You can calculate, but it's not so popular, and that's why sometimes it's not something that is not like now. Most of the things, if you put it in people's book now, things that are not popular, people just say, what does it mean? But if you now ask for it, just like somebody was asking, he said that if you put a median, if you put it a quarter rate. So that one, there is just some little calculation to get its first size. For t test, for chi-square also there's effect size. So but what I would do is that maybe in the slide I will just include those effect size. How to do that. But most of the time, all of them, they are not, you will not see it in the, you will not be able to run it with SPSS. No, those are new advances, and as people are reviewing their software, they will now include it. It's just like when we did the non-parametric counterpart of the ANOVA the last time, this Kukawalis. You know, if you find a difference, or like the ANOVA, if you find a difference, you use post-op. But their own post-op, you cannot run it with SPSS. It's just some formula, jaga thing, you just put, you feed into it to find out. I don't know if I have communicated now.
Yeah.
Hello? So any other question?
No.
Okay, let's proceed. Let me reduce the volume on that thing. The last one is a median test. So this one is quite interesting. This median test is a non-parametric test that is used to test whether two or more independent, can you see two or more? So two or more independent groups differ in central tendencies, specifically whether the group have been drawn from a population with the same median. So this median test now is non-parametric counterpart for independent t-test and for ANOVA, one-way ANOVA. So that's why I say from two or more group. So two group is for t-test, more group is for ANOVA. So you go for both two independent group or one way independent ANOVA. The principle of the test is that if two samples have the same median, they should have more or less the same proportion of observation above and below that median. What it means that if you have two samples, if the median is the same, so if you mingle them together, it will still be that median that will be median. So do they have, if they have the same median, if you now merge them together to have that central median, so equal above the median, they should have the same number. Each of them should have the same number above the median and below the median. That is the logic. This will be true irrespective of their two distribution. If any score fall at the value of the combined median, they may either be dropped from the analysis or included with a score less than the median. Just like what we did the other time when we were doing Wilkinson sign rank test. Once anyone is 0, that is the same value, because you remove median from each value to really know which one is above, which one below. So anyone that is the same, it will be 0, is out of the game of the calculation. So no alternative to median test when dealing with sensor data. That was what I said before. Sensor data is seen in survival analysis. In survival analysis, the outcome of interest is time before an event. Time before an event. That is what you measure. Because sometimes the event might not have occurred when you want to analyze your data. So in that case, you say time before an event. You can only know time before an event for some if the event has occurred in that person or in that subject. So the time you are analyzing now, you follow with time you are analyzing, if the event has not occurred for that person, is sensor, because you don't know the time before the event. But for the one that the event has occurred, you'll be able to say, oh, it's 3 years before, it's 2 months before, 4 years before. But if the event has not occurred, like for example, now if death is the event, anybody that has not died, you cannot say this is the time before the death of that person. Or if it is maybe relapse after you have treated cancer case. If it has not relapsed in some people in your data set, you cannot say this is the time before the relapse. In that case, for those data, it's called sensor data. And median test is the best. So it has no equal among all these non-parametric when it comes to sensor data. I think that is where it's more useful. Let's look at example. A private bank is interested in finding out whether the customer belonging to two groups differ in their satisfaction level. So we have two groups, the people that have current account and people that have savings account. They want to see if their satisfaction is the same. So they administer the question on satisfaction and they add all the score of those questions together. The two groups are customers belonging to current account holder and savings account holder. A random sample of 20 customers for each category was interviewed regarding their perception of the bank service quality using Likert scale, ordinal scale statement. The score of 1 represents very dissatisfied, a score of 5 represents very satisfied. The compiled aggregate score for each respondent in each group is tabulated as. This is an example of the one for non-parametric, because you will say that this type of scoring is not quantitative because you cannot have decimal unless if they have calculated average score. Then in this case, this is aggregate score. So this is the type of thing you say, oh, you cannot use non-parametric, you cannot use independent T. Let's use median test. This is just a perfect example for it. So look at the score now. You have 20 on this side, 20 on this side. It's very simple. the first task in the median test is to obtain the grand mean. You have to know the grand median rather, not mean, median. So if you arrange all of them in this first table now, arrange all of them in from, can you see, from the biggest to the smallest? Can you see? Can you see? From 86 was the highest, down to the lowest score is 20 here. Can you see? So if you rank each of the score, you will see that you rank from the either the biggest, or you rank, let's say you rank for, look at the if you rank it from here, you want to see the median. The median will be the one number 20 and number 40, going to be 62 and 61. Can you see? So 62 plus 61, notice all this even number now, there are, because there are two that are the median. If let's say it's odd number now, it's only one of the median. So 62 plus 61 divided by 2, that will be the median. The median is 61.5. Now, if you now say, among all of them, which you want to know how many are above the median, how many are below the median, all you need to do is just to the minor look at it. The blue, if you look at, is the same data set I show here that is here now. All the blue, they are above the median. All the red, they are below the median. So you now count in the current account group, how many are above? Look at this table now. How many are above the median? There are 8 that are above the median. 12 are below the median. For savings account group, there are 12 that are above the median, and there are 8 that are below the median. You had everything. So what it does is to give you 2 by 2 contingency table. All you need to do is just to calculate chi-square. The median statistic here is chi-square. It will sound funny to you. So that's all. So if you calculate the person chi-square, I think I put it here. Look at it. So it has given you 2 by 2 contingency table. If it is 3 groups now, it will give you 2 by 3 contingency table. If let's say you want to use it for ANOVA now, like counterpart of ANOVA, where you are having 3 groups. So what will happen is that it will divide each of them into 2, above and below the median. So if it is 3 groups we are dealing with, it will give you 2 by 3 table. No, we have already said that you use this thing for both. It's a non-parametric counterpart for both the independent test or ANOVA, one way or another. So in this case now, if it is for you are dealing with 2 groups, it will eventually give you 2 by 2 table. So like normal Pearson chi-square, the way we calculate it, observed minus expected square, when you calculate it, you get the chi-square will be 1.16, and the degree of freedom is 1, the number of row and number of column. So in this case, of course, you know the critical value for degree of freedom 1 is 3.84. So you can see that it's not, it cannot be statistically significant if you go and check the table of chi-square. So let's run it. It's quite interesting. Let's run it. So any question before we run it? Any question concerning that? That's the last exercise for today. Any question concerning that?
Thank you very much, sir. So you were saying that if it's now through, let's say it's current savings, and let's say there's one other type, current, let's say
and that's a corporate,
corporate,
or
let's say we have 4 steps. Let's say we have 4. So that is what we are going to do. Is that if there are satisfaction scores for those 4 banking types of accounts, what will happen is that we now have to rank everything from that current to the, let's say, corporate or the 4th one.
Yes, yeah, rank everything. Yeah.
We now get the median.
The median, yes.
Probably be the midway of the total.
Yes.
Okay. Then when we now want to draw the table, what it means is that we now have like 2 by, that will be a 2 by 4. Abi? 2 by 4.
The 2 by 4, yes. If there are 4 groups, it will be 2 by 4. Okay. If there are 3 groups, 2 by 3. It has to be 2 by something. That since the 2 is about above and below the median. So the other one will be the number of groups you are dealing with.
Okay. Okay, thank you very much.
Yes, let's run it. Any other question?
Well, this is just.
Yes, you wanted to say something?
No, sorry.
Go on.
That's what is above and if you get a figure that is the same thing as the median.
Yeah, you can click below. You ask it's below. No, I said it in the statement. You see below.
If it's the same thing as the median,
it will be below. Look at what if you remember, it will, you now consider it as below or less. If you remember what I said. Look at the second to the last statement, bullet point here. If any score fall at the value of the combined media, it may either be dropped from the analysis or included with score less than the media. You see now?
Okay.
And that one will not have any significant effect because it's going to be few, maybe one, and you cannot change, just like you are calculating chi-square. If the one size change by 1 to the other side, it will not change anything. Not change the value significantly. I think, let me just, why is this something out? So let me read it. Try open. I don't know if you can see now. This is the, if you look at it, there are two independent groups. Account type, can you see? One is maybe is current, two is savings, can you see? So it's two independent groups, so they are entered in series, can you see? These are satisfaction, 1 to 60. No, 1 to 40 rather, 2020. So analyze non-parametric. Now talk about chi-square. Can you see chi-square? Can you see?
Yes, sir. Yes, sir.
Yes. I'm coming. I'm coming. Leave this one. Just wait. You know that your this is not arranged 2 by 2 table, so the data is just like the way it is. So I think it's yes, legal independent sample. Wait, is it chi-square? No, it's not chi-square. It's median test rather. Sorry. So now is this thing we use chi-square for there? If we are doing chi-square for goodness of it. Two independent.
Okay.
This is
like the blood group type of.
Yes, that's what we use the chi-square for.
Okay.
So two independent sample. So it K related because you know what? A K independent sample because it's under K because this particular thing is used for it's both for more than 2 and more than 2. So it's not limited to the K, it's a K. Can you see now?
Okay.
So you now say satisfaction.
Okay.
Yes. Then account type is the grouping variable. Can you see?
Yes.
1,
Yes, sir.
2. 1, 2. So median. You can you see now? He doesn't know you. Are you doing Kukawalis? You know, if it is 300, you are doing Kukawalis. So you click on median. So if you don't want, just remove that code. You just say, can you see now? Oh, let me share the results.
Sorry, sir, that Tepestra, is it chi-square for trend?
No, that is a trend something. You know, we use it, we were here for ANOVA. We use it now. When we did it. If you want to know if the thing vary along the categorical, the trend. So we did it in ANOVA.
Thank you.
You cannot be talking of trend when you are talking of two groups. It's only useful if your categorical variable is ordinal.
Ordinal scale.
Yeah, it's ordinal. That one does it change along? I don't know. Like for example, now when we talk, which one did you use?
Socioeconomic.
You remember the example we used for that our ANOVA then, the libido. Libido is even ordinal because we have one group, the placebo, another do one dose, low dose, high dose. It's ordinal. So that was why we're able to do that thing. Look at the trend. Look at it. Look at the chi-square. Look at the whole chi-square 1.6. Isn't that what we get in the other one? And the p-value. Hey, look at it. 1.60. And also give you the median there. Can you see the median? 61.5. That's what we calculated at the median.
Yeah, that grand median.
They also give you yet correction chi-square, but if the one is not yet corrected is this one. If you correct it will be. So any question?
Thank you, sir.
So interesting. Very interesting. Any question?
It is.
Any question?
I don't have any. I don't know if any other person.
Okay.
Thank you very much.
There's no other question. Any question from any quarter?
Not concerning this one, but for tomorrow's own. I requested for something. I requested for a module for tomorrow's.
Yes, I answer you.
Because without a module,
it is not ready.
By the time you finish, you will forget.
Sir?
I know I got the answer now. Not reminding you, I got the answer.
Okay.
I got the answer.
Dr. Sholu was
Can we break for today? The brain has become saturated.
I did the module. If you remember, when I came to Bielsa, even before that, I have completed that module I share with you. The examiner. Most of all these things I prepared them. You know this issue of
no, it's not inside though. This one of a sample size is not inside.
And that's what I'm telling you. The sample size is there, but it's not elaborate. I even remove it when you even talk that I included. I've removed it before because of controversy. You know, the issue there is that statistical is not research methodology generally. So that was a better when you now demanded for it. So that's why I now get more into it. Yes, I mean, because I don't want people.
Sometimes
what did you say? What did you say?
You taught us practically how to use the WinPepi to calculate sample size, but it wasn't in the module, so all of us.
And that's what I'm telling you. Yes, I said that. The practical something. Yes, it's
so
not.
This time around, I wanted.
Sorry, it just went off.
Okay. I was trying to say that she wants to pay for that online. That's I told her about it. She wants to pay for that online. That's the thing I paid for, the leverage stats. Dr. Sholu. Dr. Sholu.
Yes. Is it difficult?
I told her. She was saying that she has been trying to. I told her she has to use her card. She was like, can she pay directly to your account? I said, no.
I don't know how you can help her because I've told her that that's your those are videos will help her. So I was advocating for it.
I just sent test to her. That you didn't join the something. If let's say you want to do now, that just you can just share it with us. I will just show her the way to do it.
I think in fact, she said she was so tired. I think she slept off. Because I was trying to tell her how to pay for it. But I told her she has to use her card.
You did it now. Just say her the step. I sent the step to everyone. I even sent the step to her.
Please, if you can, okay, you send the if you send the step, that's better.
I have sent the step to her now. So to everybody, I forwarded it to her.
Okay.
Because he was trying to say that there is one friend want to do one sample size something. I said that you should go and subscribe for this something. Because we have talked about sample size for about 3 weeks. You don't be asking me a question about sample size.
Thank you, sir.
Nancy is a friend. I said let the friend subscribe to it.
You never try with you. She was calling me this morning about what this thing she wants to do. That
okay, Oga, can I log out?
Oh, sorry.
You can log out and go and subscribe.
Okay.
Go and subscribe also. Yeah, Jane.
Oga, our own is lump sum now.
No.
Our own is lump sum. I want to pay 100,000 at once so that we'll be
you don't understand what I'm saying. I'm not talking of the workshop. So that you have access to the online the material. If that one, I cannot grant you access unless you subscribe. I don't know if you understand me now. It's automatically you now have access to all the lecture.
I understand that one. I can subscribe. I'm trying to fund my Naira account so that I can use it to subscribe.
Okay.
From what I saw there, I have to put the number on my ATM card.
Okay. Of course, now you have to. It's space stock.
Yeah,
no
so
problem.
I will fund my Naira account and use it. I saw the procedure you followed the other day, so I will follow it to go and subscribe.
Exactly.
Because all of this training is only when you go back again and read the manual over and over.
The logic behind it was why I want everybody to do that is that is in the process when you are watching it at work or sometimes somebody this is interesting. You want to get it. I don't know if you understand me now. That's why I want people to be on it here. Okay, no problem. You can log out.
I will subscribe. I will subscribe, sir.
Okay, no problem.
Thank you.
Okay. Good night.
Thank you, sir.
Good night.
Okay, good night,
sir. Good night,
everybody.
Good night.
Good night, everybody.
Okay, good night.
Yeah.
Well done. Good night. Dr. Balogun.